So, as a part of our excursion series in mathematical physics, we now take up problems on Stokes' curl theorem. Similar to Gauss's divergence theorem discussed earlier, Stokes' curl theorem also plays a very crucial role, very important role in different branches of physics. Again, most importantly, being uh, electrodynamics and fluid mechanics. So, the statement of the theorem, this theorem historically was proposed initially by Lord Kelvin in 1850, and in the existing form, the way we see it today, was proposed by Stoke in 1854. And it is also very interesting anecdote how this theorem first uh, came to light in general public. In mathematical tripos examination, Stoke asked this theorem as a question for the first time without any background before. So you can understand Cambridge University's mathematical standards. I'll put uh, a special reference for those evidences, historical evidences, or maybe we'll talk in some other clip exclusively about history of these fundamental theorems. So coming back to curl theorem, Stokes curl theorem, its statement is line by line. The line integral of a vector field f around a closed path C is equal to surface integral over any surface S that has C as its boundary. So suppose you have a vector field F and C is the closed loop. So you calculate closed path line integral of this vector field F. This is, according to curl theorem, Stokes theorem, equivalent to a surface integral of its curl over the surface S for which C is serving as a boundary. Now, these type of surfaces has a very special name referred as capping surface of closed loop C or closed path C. So now a very interesting thing I would like to point out. In fact, that is where I want to emphasize with some of the problems here, that whenever you are having a closed loop C, the choice of capping surfaces is not unique. For a same circular loop C here, you can see a straightforward disc-like surface S1. You can also see a hemisphere-like surface S2 and a cone-like surface S3. All three of them are capping surfaces of same circular loop C. Now, if we generalize this statement and say we have n such capping surfaces for a given closed path C, then right hand side is equal to curl of f dot dA over S1. It is also equal to curl of f dot S2. Likewise for Sn. Now this particular fact has got a immense physical importance. As some of you can recall, when James Clerk Maxwell proposed the correction in Ampere's law, his argument was exactly same. He had a loop C. For one capping surface, his story was different. For another capping surface, his story was different. So, from mathematical point of view, Stokes theorem played a very important role in the development of that particular correction by Maxwell. So now we will take a very simple and one of my dearest vector field f as simply phi cap. Phi cap being the unit vector of uh, cylindrical or spherical system, azimuthal variable that can go on 0 to 2 pi. So taking this as an example of a vector field and taking a closed path C like this, we will work out explicitly Stoke's theorem, and then we'll take a variety of capping surfaces for same loop C, and it will be a good example to appreciate basic essential idea of this great mathematical result. So let us first calculate the left hand side of our theorem, that is f dot dl over C. In this case, I am having my vector field that is f equal to phi cap, just phi cap. This will become phi cap dotted with phi cap a d phi. The length element dl on a circular path of radius a will be phi cap a d phi, and the limits for phi will run from 0 to 2 pi. So f dot dl over this turns out to be simply 2 pi times a. So this is the left hand side of our theorem. Now we'll calculate curl of our vector field, because that is needed to evaluate the right hand side of our theorem. So curl of f in cylindrical system, I can write it down for a general vector field f, that is 1 by s cap, partial derivative with respect to s component of f, s times phi cap del phi s times f phi. Note that scale factors for cylindrical system are 1, s, 1 respectively. So all the product of scale factors comes here, and scale factors are multiplied here in the first row with each unit vector and also with the corresponding components of the vector field. So this is how a general expression of curl of a vector field f look like in cylindrical system, in cylindrical variables. So for our given vector field, I can simplify this: s cap del s 0, s times phi cap del phi. Phi cap coefficient is 1, so it is simply s, z cap del z, and 0. So curl of our phi cap vector, curl of phi or curl of phi cap vector is simply z cap by s. Very interesting result. This will note. So curl of f one should not underestimate at s equal to 0. This has got lot of issues that we can discuss it some on some other occasion. So having calculated curl of phi cap, that is simply z cap by s, we now take surface S1 as our first capping surface. S1 surface is a circular disc lying on xy plane. So it has got an area element dA, which is z cap s ds d phi. So I can work out curl of f dot dA S1 over S1. So this is z cap by S, and the area element z cap S ds d phi. And not to forget, our limits will go for S 0 to A, radius of the loop, and azimuthal variable full limit 0 to 2 pi. So curl of f dot dA over S1 surface is easy to see, 2 pi A, which is equal to left hand side of the theorem which we just calculated. So next we'll change our capping surface to a hemisphere as depicted in this picture. Note some important thing. This is our original boundary C of radius A. The moment I take hemisphere as a capping surface, this A turns out to be radius of that hemisphere, because I have kept my circular loop on z equal to 0 plane, or you can say theta equal to pi by 2 plane. Further, because our loop is counterclockwise, the capping surface will be interior of this, and hence it is always pointing out radially inward. It is always inside the always pointing toward the center of the hemisphere. This is very important when you consider this type of capping surface. So now, because my geometry of my capping surface is spherical, it's a good idea to calculate, or rather recalculate, curl of phi cap in spherical polar system. So this is a general expression you can recall again, and with the help of this I find curl of f in spherical system as this much: r cap by r sin theta into cos theta minus theta cap by r. So for S2 surface, I can immediately plug in everything in the integral, and note, well, when you substitute everything in the integral, notice for a hemisphere, limits of theta will run from pi by 2 to pi by 2 to pi. So I can invert this pi by 2 to pi in my next step from pi to pi by 2 and change this minus sign to a plus sign, and you can see straightforward my answer is 2 pi A, as I had done before. Now the last capping surface that we consider for the same loop C as this type of conical surface where this radius, I mean it's a part of a sphere of radius capital R, and this is my capping surface, the loop C, and interior of this cone is my capping surface in this case. And why interior? Again, the same argument goes as we had done in the case of hemisphere, because we have a counterclockwise loop, so interior of the surface is our capping surface, always pointing towards the negative theta direction. So area element in this case, I can write it down recalling my curvilinear coordinate system, negative sign with this argument, and it is theta cap r sin theta dr d phi. Minutes before, we had calculated the curl of phi cap, curl of our vector field, that is r cap by r cot theta minus theta cap by r. So definitely when I take f dot dA, only this term survives, and this becomes r equal to 0 to capital R, phi equal to 0 to 2 pi, 1 by r, and r sin theta d theta d phi. This is we are working, our capping surface is lying at theta equal to constant. So this is a case of theta equal to constant surface. Previously it was r equal to constant surface. So when I integrate it, this sine theta remains as it is. Dr will yield a r overall, and phi will bring a factor of 2 pi. So it is 2 pi capital R sine theta. Now note, this greater circle is having a radius small a, which is exactly equal to r sine theta. I mean, this is like you have a globe, you put a small circle on the top and let it come towards the equator. So radius of those circle will start increasing. It will reach to a maximum at z equal to 0 plane, that corresponds to theta equal to pi by 2 as capital R, the radius of the sphere itself. And then again it will shrink for higher values greater than pi by 2 all the way to pi, it will shrink to a point. So in this sense, we have taken a simple example of unit vector of a spherical, polar or cylindrical system, and by taking a variety of capping surfaces, we have appreciated that non-uniqueness of capping surface is one of the most striking feature of this beautiful result of Stokes theorem. I strongly feel most of the time it is neglected. People just state it out, work out the problems, and they just move ahead. It is important sometimes to slow down and appreciate these small things. So we'll meet again in similar exercises next time. Thanks very much.